This is an exciting development in how this software is working. But it looks like we've got something going on. Alrighty. Oh, there we go. That'll help us out more. It would also help if I wrote with the pen and not the eraser. Though before we get too much into this, do folks have any questions about the usual sorts of stuff? Like number 8 on the homework. Absolutely. I'll just need to pull it up real quick. Man, my keyboard's really loud. Number 8 on the homework. Alrighty, so this was a concave up, concave down, points of inflection. Alrighty. Let's see. Yeah, I think this will work out. We'll have to see though. Right, so what do we need to find in order to talk about concave up, concave down, and inflection? There we go. Maybe there'll be less of a not quite. Critical points are very closely related. Right, so the derivative will be a step along the way, but what do we actually need for concave up and concave down and points of inflection? Right, the first derivative gets us critical points, which are related, but aren't actually any of those things. So what do we need to look for concave up, concave down, and points of inflection? So we looked at two different things when we were talking about this stuff. I've told you it's not the derivative, so what's the only other thing we talked about when we talked about finding the shape of the graph? Nope. We did not talk about that in the sections when we were finding intervals of anything. And they're not particularly related to critical points. Other than the fact that the derivative gives you the tangent line. Also, if we were looking for the tangent line, then the derivative would be what we'd need to find. So concave up, concave down, and points of inflection require us to find the second derivative. Right? That whole section where they come up is all about how we can use the second derivative. Right? So we're going to be finding the derivative along the way, but what we're actually looking for is the second derivative. So this is a product of two functions. So we take the derivative of the second multiplied by the first. And then we take the derivative of the first multiplied by the second. Right? And we know we want to take another derivative because concave up, concave down, and points of inflection have to do with the second derivative. So I'm going to combine these into one term because that way I only have to use the product rule once instead of twice. So finding the second derivative, I'm using the product rule again. I've got this guy multiplied by this guy. So the derivative of the first, derivative of the second times the first, plus the derivative of the first times the second. And what do I want to do with this second derivative? What am I going to need to be looking for to find where it's concave up, concave down, and points of inflection? So I mentioned that it was something related to critical points, but not actually critical points. Right? Critical points have to do with the derivative. So if I'm getting something related to critical points, but having to do with the second derivative, what do I need to do? how do we find critical points? We find critical points by setting the derivative equal to 0. We find potential points of inflection by setting the second derivative equal to 0. And if we want to find something's equal to 0, it's helpful to factor. Right, which means for 1, combining like terms. Then we can pull an x out. And there we've got a quadratic, right? So either x is going to be equal to 0, e to the 5x is going to be equal to 0, or this admittedly kind of obnoxious quadratic is going to be equal to 0. Well, those first two are thankfully pretty easy. Right? If x is equal to 0, then x is equal to 0. That's one potential inflection point. Is e to the 5x ever 0? I'll let that sit for a while I start to use the quadratic formula over here. I gotta bring out my calculator a little bit. Oops. Aha. Turns out it's not going to be as obnoxious as we worried. Right? Because this guy is negative. Right? And if that guy's negative, there's no solutions here. Alright. And we don't appear to have volunteered anything for this guy, but there's no solutions here either. E to the anything is always going to be a positive number. Right? So in this case, our only potential point of inflection is 0. Right? Unfortunately, points of inflection are not quite as nice as critical points. Right? If this had been the first derivative and we were finding critical points, then 0 would just be a critical point and we'd be done. Right? But for points of inflection, we've got to do the whole number line thing, because a 0 or a does not exist of the second derivative is only an inflection point if it goes from positive to negative or negative to positive. Thankfully, in this case, we also want to know concave up and concave down, which is also given to us by finding this number line. So what's our favorite number less than 1? I'm going to choose -1 just to get us rolling. So I plug that in up here and get -1 e to the -5, 75 times -1 squared, plus 54 times -1, plus 18. So negative e to the -5, that's a negative number, because e to the anything is positive, and if we negative it, then it becomes negative. -1 squared is +1. That -1 turns it into subtraction. So this guy right here is positive. This guy right here is negative. And when you multiply something negative by something positive, you get something negative. And then we need to pick our favorite number bigger than 0. And I'm going to go ahead and pick 1 here. Because that really just means that all of our x's disappear. Right? So unless you have an x sitting around by himself, in which case he turns into a 1, all of your x's can just disappear if you choose +1. So this is a positive number, also positive, so this is positive. So, since we have a -1 on one side, so since it goes from negative to positive, then it's an inflection point. It would also be an inflection point if it went from positive to negative. The key is that it changes. So if it had been negative and negative or positive and positive, then it wouldn't be an inflection point. But since it changes over, we know it's an inflection point. And we're not on top of our game remembering the rules today, so I'm not going to spend too much time on it. But if we look back at that section, then the function is concave, up on 0 to infinity, because that's where it's positive. Yep, just making sure I'm remembering the rule right. And it's concave down on this portion of it, so negative infinity to 0. One thing, I believe that's the homework problem. Let me see if I can't check this real quick. Yeah, so this is one, I'm going to do a fake problem like we just done some work. Right, so when you're wanting to do multiple open intervals in one answer, so for instance, concave down here is going to be on 0 to 1 and 2 to infinity. And when you want to do something like that, where there's multiple open intervals, you need to put a union in between them. That's how you add multiple intervals together. And then concave up is going to be infinity to 0, unioned or added with 1 to 2. Right? And the other thing that's sort of different about this guy, right? So pretending like we had the same f of x for some reason, right? We can see that we have inflection points, all three of those give us inflection points. Right, and usually we just talk about inflection points with the x coordinates. Right, and say that we have them at, right? This was technically probably bad grammar. Right, because it's only at those x values. If I wanted to say the actual points, I need to get an x coordinate and a y coordinate. That's what points are made up of. So, I'm going to give us a different, here, this was going to be f of x equals, I don't know, x squared plus 5x minus e to the x. So if I wanted to find the actual points, then I would take that x coordinate and then I would plug it in here. Right. I would take that x coordinate and I would plug it in here. And one of these days I'll write something down, right? Alright, so this point would be 0, negative 1. This point would be 1, 6 minus e. And this point would be 2, 14 minus e squared. Right, so that's the type of answers that third question is actually looking for. I forgot how this problem wants things formatted. Right, but if something asks for an actual point, then that generally means it wants both coordinates, right? If it says, where are there inflection points, right, then it wants to know where the inflection points are at, and then the x coordinates by themselves are generally fine. Right, but points have two parts. They have an x coordinate and they have a y coordinate. So that's some notation stuff specifically for the homework thing. That's probably way too small to be helpful, but are there any questions about anything we did there? Anything we want me to zoom in on? Any other questions about stuff? Alrighty. Well, let's zoom ourselves back in. So with this section, it's all talking about Newton's method. Right, and so on the surface, Newton's method is about finding zeros. Right, so figuring out where a function is equal to 0. Right, we can also use it to approximate certain transcendental numbers. Right, the ones that have a infinite decimal. But the point of it is for finding 0. So if we want to do something else with it, we're always going to need to reframe it in the terms of finding a 0. Right, so the basic idea of it let's see if I can do this. Right. And so if I start here, right, then that's not the 0. That's clearly not. The 0 is somewhere over here is what we're trying to get to. Right? But the idea of Newton, I might not have made this steep enough, right, is that we go down to the function, right? So this is going straight down. And then we draw the tangent line. Right, and we figure out that that's going to hit the x-axis somewhere. Right? If it's properly the tangent line, it's not going to hit the function again, but it will definitely hit the x-axis. Because every straight line, other than completely horizontally flat ones, hits the x-axis. So we're going to pick this point here and have it be our next point. And we're going to do the exact same thing. I'm going to zoom in a little bit here. So we're going to go up And we're going to get a point on the function. And we're going to draw a straight line, a tangent line rather. And so that doesn't quite, maybe this will work, get us the 0, right? It gets us something else, but we're getting closer and closer, right? So this becomes x2. We follow it up to here, and then we've gotten too small for me to really do on this picture. But that's the idea that we're doing here, is we're picking a point, we're dragging it down to the function, we're taking the tangent line back up to the x-axis, and that gets us our new point. Then we're going to take our new point and do the exact same thing with it. We're going to drag it up to the function, we're going to get the tangent line to drag us back down to the x-axis, and that gets us our new function. Right? And how we're going to do that is the formula where each function, or each point, is the point that came before minus the value of the function at the point that came before divided by the value of the derivative that came before. So to do Newton's method, we just need to find one derivative and then plug a whole bunch of stuff in. So the Newton's method is the word just flew directly out of my head. And I can't retrieve it. But your best bet whenever you're doing Newton's method is to definitely use a calculator. Right? So once you find that derivative, it's just going to be a matter of plugging a bunch of numbers into the same function over and over again, and working with it. But the real calculus work comes in finding the derivative. So the first thing you need to do with the Newton's method problem is find the derivative. Then you need to plug some stuff in. So what do we need to do first when doing a Newton's method problem? What's the calculus part of a Newton's method problem? Derivative. Yeah. So we're going to want to use this formula. So we need to know, in addition to f of x, what is f prime of x. So it's just a polynomial, so it's a matter of using the power rule a lot. Well, a lot. In times. And so we're going to perform 3 iterations. So we're going to want to find x1, x2, and x3. Right, and one of the things about Newton's method is that you always go in order. Right, you start with some x0, some x0, and then the next thing you find is x1. So what should x1 be? So we have this formula up here for finding x sub n minus n plus 1. So if we're looking at finding x1, and we have a formula for xn plus 1, what is n going to be when we're trying to find x1? What do you need to add to 1 to get 1 back? Well, hopefully it's 0. Right? So that means if we're looking back up here, right, we want to find out x0 plus 1. That means at the end we need to plug in, and these other 3 places needs to be 0. Right. And I'm actually going to move this out. Whoops. That's not what I wanted. Whoa, that's bizarre. Okay, there we go, that's better. Right, so we know that x sub 0 is negative 1. Right, and if we plug negative 1 in up top, And then we plug it in down below. And we get -1 minus. All this stuff up here just becomes -1. This, the -1 squared becomes +1, so we get 5. So x1, right, because that's what we started off trying to find, is going to be -4/5. Any questions about what we did there? So the problem says to perform 3 iterations. So we need to do this a couple more times. After 1 comes 2. So what do we need to plug in for n here? So again, if we're trying to plug into this formula, right, that means we need to take the thing we're looking for and write it as n plus 1. Use that to figure out what n needs to be. And then plug that in into all these other places. So if we're looking at x sub 2, yeah, there we go. Right? 2 is 1 plus 1, so we're going to plug in 1 to all those places. Alright, so it's going to be -4/5 minus -4/5 cubed minus 4/5 plus 1. 3 times -4/5 squared plus 1. Whew, okay. Let's see, I think I worked all this out somewhere. Wait a second. Y'all are supposed to catch me when I make silly typos. That's not a 2. That's never a 2. That's supposed to be that one right there. Just got done erasing those and I put them right back. one last thing to get rid of before that never happened. Except in that entire recorded instance that just happened there. So if we cube that out, I'm going to go ahead and multiply this top and bottom by 16, and this one by 64, just so we can add that all together. Down here, I'm going to go ahead and turn that 1 into 16 over 16. So all of this adds together to get negative, whoops, first we need this negative 3/4. Well, that is a thing we got there. And I don't know about you, but I don't like complex fractions. But thankfully, the small denominators, right, these guys here, have a common factor, right? So if I multiply both by 64, then if I multiply the top fraction by 64, I just get negative 11. Right? 16 cancels with 64 with 4 left over. So I got 4 times that 43. Right? Now again, one more time, I need to get common denominators. I'm going to go ahead and bring these two together to make it positive. Whew. So, we've got, well, maybe we can go ahead and multiply that out. I think that sounds right. Okay. So, we've got our x sub 2. Man, do I not really want to have to go through that again. But the problem says we want to do 3 iterations. And what's n going to be in this case? Two. Yeah. Now, I don't want to do all that algebra by hand. And Newton's method is a numerical method anyway, so these are really sort of designed to automate. So what I strongly recommend for Newton's methods problem is to get you a calculator. Right? Especially if you can get one that stores variables. So let me make a note for myself. Yeah. So I found one that we're going to use today. That also lets me do functions. So, oops, I'm going to call f of x, well, I need to go back here again. X cubed plus, what did we say? X plus 1. It doesn't really have anything for taking derivatives, so I'm just going to call the derivative g. And we said that was 3x squared plus 1. And now that I've done that, I'm going to make, well, it was x2, so I'll make it be the second letter of the alphabet. Oops, I missed a digit. Right. Oh, hey, it'll even simplify for us. This is a pretty nifty calculator. And then I know that my next one, the last one that we want, is b, so x2 minus the fraction f of b, g of b. And so we get our answer here. It's not giving it to us in nice fraction form. Might mean that it just has too big numbers. But for these problems, for Newton's methods problems, the idea is to approximate a zero anyway. So giving it a decimal form is fine.